Entschuldigung, mein Deutsch ist nicht so gut, so I'm going to be carrying on in English, unfortunately, so sorry to anyone who's not going to be following. That's how I have to start every single class that I ever teach, so I'm getting used to it. But it is really nice to be here, speaking in front of an audience where I don't need to waste the first 10 minutes explaining how devastating climate change is and how devastating it's going to be for our future generations. Because now the vast majority of people are starting to know, and in fact, this is probably the only number that I'll give you that is vastly out of date. I'm sure this number is much higher than we've got up here, because everybody now recognizes the threat of climate change. But the real challenge of scientists is no longer trying to prove to everyone that it's happening. It's in fact trying to find tangible solutions that can get us all engaged. Because the atmosphere we're dealing with, as a very basic intro, is extremely thin, like the width of the rubber on a balloon. It's unbelievably thin and vulnerable. And every year, we emit about 10 gigatons of carbon into that space. That's like 10 trillion tons, or 27,000 Empire State Buildings of carbon every year. Now, some of it goes into the land, some of it goes into the oceans, but a large chunk of it, as we all know, stays in the atmosphere, and it's building year on, year out. And as a result, since the start of the Industrial Revolution, we've increased that burden by about 300 gigatons. That's 300 trillion tons. Now, you can see here, there's two chunks of numbers. Clearly, cutting emissions has to be our absolute priority. None of this comes at the expense of the immediate and urgent need to cut fossil fuel emissions using technological and innovative solutions. But if we want to capture the 300 gigatons that already exists up there, we're going to need an immensely powerful system. And as you might have guessed from the introduction, the most powerful system that we have to date is the natural system. So this is a NASA simulation of the carbon cycle, one that we've built and we use very frequently in our lab. And we spend, and you can see here the very high concentrations of carbon indicated by red colors in the high latitude parts of the world. And this is in sort of early spring, from winter into spring. But as you see, as we tick on into late spring and then summer, these colors disappear. And that's caused by one simple process. It's the emergence of leaves on trees. The simplest ecological process that every single one of us, particularly in the Northern Hemisphere, are very familiar with. We're just about to start losing those leaves now. And it's one of several massive ecological fluxes that balance one another out to regulate our carbon cycle every year. So a few months later, that carbon will be emitted back into the atmosphere as those leaves fall and decompose. Given the massive scale of this system, relative to the quite small anthropogenic emissions, managing it effectively has to be one of our best chances to manage and capture that 300 gigatons that I mentioned earlier. But in light of that exciting observation, it doesn't really change any of our perspectives. We've all known that trees are fantastic. We all have a lovely connection to forests, and we feel like nature is a very good thing for us. But the problem is it's never been seen as a scientific or tangible option, for the really simple fact that we've never had any quantitative idea of what's actually possible. So we all know that planting trees good, plant a tree, save the world, we've all heard it before, but less than 2% of climate change funding, climate action funding, goes towards natural climate solutions. And again, that's because who's going to invest genuine time and money in this solution until we have any idea what we're actually going to be achieving? So if we look at the top climate change solutions, an organization called Project Drawdown does a great job of listing the top solutions in terms of how much carbon they would save or how much carbon they could draw down. And so the top of the list is effective refrigeration management. If we all recycle our fridges and capture all of the aerosols that come out and also upgrade to the best and most efficient fridges, we have the potential to save 24 gigatons of carbon by 2050, which would be fantastic, a wonderful goal. Obviously, if we prevent our meat consumption, we could save 18 gigatons by 2050, another very exciting and hopeful movement. But the value of global restoration has always been way down on the list. And that's, again, because we have no quantitative idea of what's possible. So ecosystems have been broken down into small parts that are listed way below those top solutions. So we've been trying to address this and try to overcome this massive uncertainty in the power of natural climate solutions, to decide if we really should be investing our time and energy in this, or if it's just a nice thing that we do on the side. But the main challenge is, as you can imagine, that the Earth is massive. So getting a handle on the scale of this system is really difficult, because we've relied heavily for the last couple of decades on satellites, which have spectacular global coverage. They cover every single corner of the Earth, but they can't see below the canopy surface. So while they tell us if it's green or not, they don't tell us how many trees are there, or what the structure of those forests are, or how big those trees are, or which types of species are there, let alone what's going along below the soil, which is determining how those forests grow. So until recently, there was a previous NASA estimate that there was about 400 billion trees on the planet. And that was the basis for the UN's Billion Tree Campaign, which is a very exciting campaign to restore 1 billion trees to save the climate. But again, this is based purely on satellite observations from above. And so quite simply, we knew that we needed a new generation of model, one that's built from boots on the ground. Now this is quite hard to see, but there's 1.2 million dots on this map. And each of these dots is a place where somebody has stood on the ground estimating how many trees there are in that little plot. Pretty simple information. And using basic machine learning and artificial intelligence, we can now tie these dots together based on variations in satellite signals, but also climate characteristics and soil characteristics, which allow us to predict how many trees there are in all the areas that we don't have dots. And very simply put, this allows us to generate a global quantitative understanding of the Earth's ecosystems for the very first time, showing that there are in fact closer to about 3 trillion trees on the planet. So that just sort of puts into perspective the scale of this system. And it was, again, very exciting news when this came out. The UN's Billion Tree Campaign was ingeniously renamed the UN's Trillion Tree Campaign. So we're now aiming to restore 1 trillion trees, which is going to have a much bigger impact. But it doesn't just tell us how many trees there are there. We also know the size of those trees, because those people on the ground can measure the size of the trees. So we know that there's amongst this 3 trillion trees, they store about 450 gigatons of carbon, just in the above ground parts of the trees, just in the living biomass of that tree. And again, I'd like you to relate that back to the 300 gigaton problem that we're talking about, just so you understand the scale of the system we're talking about. So there's about 450 gigatons of carbon in there, but these models don't just tell us where trees are now. By describing how environmental characteristics shape ecosystems, they can also tell us in which environments trees could naturally exist. So we can simply model where trees could exist across the planet. And now obviously most of that land is covered by existing forests, or by urban land or agricultural land that we need to feed an ever-growing human population. But when we remove those lands, we're left with something quite unique, quite interesting. These are the 0.9 billion hectares of degraded lands around the world. It's hard to have a definition for all of the millions of types of degraded lands, but these are effectively regions around the world where trees could naturally be growing under today's climate, and yet they're not because of some human activity. Maybe we've grazed some cattle and moved through and the soil's been degraded, or we built a golf course that was abandoned, or infinite possibilities. But ultimately, these are regions where forests would naturally exist, and even though we're not using them extensively for urbanization or agriculture, trees aren't existing there. And what we can simply calculate, now we know where that land is that in that area, if we were to restore trees across all of those ecosystems, that 0.9 billion hectares, we'd be able to capture a staggering 205 gigatons of carbon. So that's obviously vastly, vastly higher than we might have previously expected. Now, of course, the first thing that people will say in the correct consideration is that this would obviously take a really long time to accumulate. Over 100 years it would probably take to accumulate that 205 gigatons of carbon. But as soon as those trees are in the ground, not only are they immediately capturing carbon from the atmosphere, but they're also producing water vapor, which forms clouds, particularly around the tropical regions. Those clouds reflect a lot of the sun's energy away, with an immediate cooling impact on the atmosphere and the climate. So not only is the full potential of restoration extremely exciting, but there's an immediate positive cooling impact that happens all around the world. And that's not even including all of the thousands of benefits like ecosystem services that comes to human livelihoods and biodiversity around the world. And the nice thing is that it's a map, so you can zoom into your area of interest and understand what kind of impact you can have. If you zoom into Germany, you can see there's about 3.5 million hectares available, which is about 9% of German land, available for forest restoration. Now, I'd highlight this this bar along here. It doesn't go to 100%. So a green area doesn't necessarily mean you could restore 100% forest, but it certainly means you could get a couple of trees in there, and when added up, they could capture almost a gigaton of carbon. So you'd be getting about 0.5% of the global total by contributing just in the country of Germany. And obviously, given this exciting new information, we now know the scale of this system, there was suddenly an explosion of media interest. We had hundreds of millions of dollars pledged towards forest restoration, particularly around the tropics. And this was followed by an enormous spike in restoration projects around the world. There's already many out there, and we were connected to about 50 or so others that have sprouted up in the last couple of years based on this quantitative new information. And now those restoration projects are all doing various different things, but they're working with local communities to try to bring benefits that involve the climate, but also water security, food security to those local communities that then work to restore and maintain those forests for long periods of time. But, as with any media explosion, there were some downsides, and quite rightly, there was a lot of opinions and a lot of chaos. And we were criticized for many aspects of the research, which mostly come from some miscommunications, but some of them highlighted really, really important points. The first criticism, that's so stupid, we can't just plant trees, we need emissions cuts. Now, as I've introduced at the beginning, I hope it's very clear that this criticism, while I don't love the introduction to it, is absolutely correct. Of course, we can't do it without emissions cuts. We need emissions cuts and carbon drawdown in combination. Climate change is way too big for us to be squabbling over climate change solutions. We need to act on all of them right now. The next criticism, a very heated debate happened over this one. No, we need to conserve existing forests. And of course, for fear of repeating myself, this is absolutely correct. This is not a criticism. This is abundantly true. Global restoration doesn't mean replacing the old ones with the new ones. Old forests store the vast majority of the world's forest carbon. Replacing them with little shrubs isn't going to do anything. We obviously need to prioritize conserving what we currently have and restoring new stuff, but they're not mutually exclusive. Obviously, they must be done in combination. And finally, the final criticism, we also need grasslands and savannas. And for fear of repeating myself, you know what I'm going to say. Obviously, this is correct. These criticisms are just absolutely correct points. They absolutely couldn't be more obvious. Of course, we need to conserve other ecosystems around the world. And in fact, these other areas were part of the motivation for our study. Because in many parts of the world, people are just planting trees all over the place. The reason we conducted this study is to identify which regions should support trees and which ones shouldn't. Because when you restore a forest in a native, natural grassland, not only do you destroy the local biodiversity, but you can also lead to the death of those forests, which degrades the soil and you lose carbon from those ecosystems, highlighting the need for a scientific basis. But in these other ecosystems, these grasslands and shrublands, the message is a little bit different because the carbon isn't stored in the trees. It's actually stored in the soil beneath those trees. And that means we've got to start building a new generation of model. Because carbon dioxide in the air enters these ecosystems through the plants. The plants ultimately, as you all know, photosynthesize. And this video is a lot slower than the pace I'd normally talk. But they obviously produce carbohydrates, which have the structural components of those plants. But a lot of that carbon doesn't form carbohydrates, or even after forming carbohydrates, enters the soil in dissolved organic carbon. And that feeds topsoil. So really the plants only serve as the carbon pump, and it's the soil where the vast majority of that carbon's being stored. So, as I mentioned, we've been building a new generation of model, this time not based on observations of trees above ground, but by millions of samples, soil samples that have been collected around the world. And very simply, using the same machine learning and artificial intelligence, along with thousands of layers of climate and soil characteristics and topographic information, we can generate a quantitative understanding of where all the world's soil carbon is, showing some quite interesting patterns. Firstly, There's way more carbon in the soil. 1,500 gigatons of carbon currently exists in the Earth's soil, and that's only to 2 meters depth. But it's also interesting, I don't know if everybody knows this, the vast majority of that exists in the very high latitude regions where cold conditions slow down decomposition. And when you have slow decomposition, you get the accumulation of carbon in the soil. So if we want to focus on forest restoration, the tropics absolutely must be our focus, because that's where trees grow really fast and capture loads of carbon. But if we want to focus on soil regeneration and agricultural regeneration, the high latitude regions have an immensely important role to play, including Germany and above. But again, these models don't just tell us where soil carbon is now. We can also model how much carbon there would naturally be. And we see there's room for an additional 116 gigatons of carbon. On top of the 200 that we already mentioned, we're starting to get at a massive carbon drawdown potential. Now, some of that does exist in the forests. So if we conserve existing forests and restore them to their natural health, we could capture about 30% of that 116 gigatons. But grasslands and shrublands cover an even larger extent. Those regions don't have the largest amount of soil carbon per unit area, but because they're massive, they actually could capture almost 40% of that 116 gigatons. And the nice thing about these ecosystems is they don't come at the expense of other land use types. So you can restore your grassland at the same time as having your agriculture. Agricultural carbon sequestration is an incredibly powerful carbon drawdown solution. And the most efficient of all of those ecosystems you might have heard of as wetlands and peatlands. These cover less than 5% of the Earth's surface, but could capture 30% of that 116 gigatons. Because again, waterlogged or cold soils don't have much decomposition, which means that carbon stays in there for a long time. So really pinpointing this 5% of the Earth's surface can have a massive impact on carbon capture. So in combination, all of these climate change solutions, well, all of these carbon drawdown solutions, paint a very nice picture relative to the 300 gigaton problem that we've got. No one's saying that this is going to absolutely solve or wipe out that 300 gigatons, but the scale of the carbon drawdown potential that we're talking about in natural ecosystems has to place them right up there with the priorities of any other carbon drawdown solution. Because not only are these effective, but they're also natural, and they're low-tech solutions, which are available to all of us right now. So they can engage the masses. We don't need incredible new scientific discoveries or technological advances. Any one of us can get engaged right now. But the big considerations are ecological, because at the moment about 30% of the trees that are planted around the world seem to make it until survival, which is a really depressing thought. Not only are we wasting time and money, but we're also degrading those ecosystems. So at our lab, we spend all of our time generating global maps that can guide effective decision-making so that these ecological mistakes don't happen. So if you're a restoration project or just an interested party, you can zoom in around the world to your area of interest, see how many trees there are, see how many trees could go there. You can see what types of species you need to plant and how many species you need to plant. You can click on your garden and see which types of species should be there. But most importantly, we spend a lot of time focusing on the soil community to characterize which types of microorganisms in the soil can support which types of trees. And with that kind of information, you can have really targeted and effective restoration. And we can even now tell you whether the forest in that area will have a warming or a cooling impact on the planet. Because in many parts of the world, forests absorb a lot of the sun's energy, and they actually have a warming impact, as many of you might know. But in the majority, they do obviously capture more carbon and they have a cooling impact. But understanding where those ecosystems are can be really valuable for guiding effective, ecologically effective restoration. But the much more important consideration, and it's very relevant in a political context, is the social consideration. Because the vast majority of restoration projects fail because they don't work in a socially responsible way. Too many projects come in and they buy up an area of land and exclude the local community from that land. This is the biggest mistake that is consistently made in global restoration, because it's completely, not only is it socially irresponsible, but it's completely unsustainable, because those people will just come back, cut down the trees and use it for their livelihoods, as you or I would if we were living in that condition. Restoration, with the amount of energy and funding and support for this, all of that needs to be funneled at least partially towards that local community. So they're benefiting from the funding that's coming from restoration. In addition, we must work with local communities so that they can benefit from the thousands of ecosystem services like foods and medicines and clean water. Some of the best restoration projects are succeeding because they incentivize local communities to promote sort of sustainable and long-term restoration projects, because it secures clean air and clean water for those communities. And when done right, it can be an incredibly impactful way to benefit, to have huge socioeconomic benefits for communities, not just in the tropics, but all across the world. And some of those projects that I mentioned earlier, those 50 projects, they are all doing this, working with their local communities to make sure that there's a sustainable future for that forest, that the community are engaged and invested in that forest. And the best of them are doing so for as little as 30 cents a tree. So if we're going to try and restore those trillion trees across the globe, if we maximized efficiency in a completely unrealistic way, we could do so for as little as $300 billion. That makes this by far the cheapest climate change solution. Given the trillions of dollars we waste every year on climate change, because of the damage of climate change, you can see this is now one that not only is cheap and affordable and environmentally healthy when done correctly, but it's also one that can engage every single one of us, because it's a low-tech solution. So we don't need to just march around in frustration. We can actually have positive and tangible impacts through the 3 simple actions of planting a tree, if you're lucky to be a landowner or you own an area that you can restore. Go out and get your hands dirty and restore a tree. And again, I said you can zoom in any location on the map and see which type of tree to restore and what soil will support those trees. You can also donate to one of the thousands of projects that are out there. With the click of a button, you can donate $1 and get 3 trees in the ground. Or just simply invest your money wisely, whether it's the things you buy or the investments you make, selectively focusing on the organizations that have a positive environmental impact can now be a tangible way of addressing climate change. So while climate change is necessarily often associated with the things that we must give up, which absolutely has a massive role in the climate change fight, we now have positive actions that we can take to actually get engaged and sort of motivate additional actions. Which brings me to my final criticism, the final criticism that we often get. This sounds great, but it's just naive. We'll never restore the entire globe. And while this message might be, again, entirely correct, it's also completely irrelevant. Because it's like saying, right, we might not achieve 100%, let's not bother with anything. If we achieved even 5% of our targets, the impacts for biodiversity, for climate change, and for human well-being would be astronomical. And I guarantee we are easily going to exceed that 5% with the thousands of people that are already restoring forests and ecosystems all across the globe. We just have to hope that the people saying it can't be done don't interrupt the incredible people that are already doing it. So with that, thank you very much.
Thank you so much for your talk. And now we can open for questions. So are there any questions regarding this talk? Yeah.
So before we heard Mr. Lindner talk about using the rainforest to plant new trees and to send the word to Germany and plant new trees again, because that absorbs a lot of the carbon, if I understood it correctly. I see a little bit a problem there, because in my opinion, bigger and older trees, they are able to absorb more carbon. So what's your stance on this?
You're absolutely correct. We need old forests, but he's also partially correct, because when you start with a small, actually, I'm going to go back to basics. If you think about a forest as a bank account, is a nice analogy. At the beginning, you're putting in money more than you're taking it out, and it's growing. So the carbon uptake by growing trees is faster. They're taking in more carbon at a faster rate. But you don't really care how fast it's going in and coming out. By the time you reach an old forest, it's in balance. You're putting in as much as you're taking out, but you've got $1 million in your bank account. That's what we're trying to aim for. So the old forests, as you mentioned, are absolutely the priority. We want to try and maximize old, large trees. But in order to get there, a forest starts with millions of small trees. You know, it's just a load of little saplings. As that forest develops, some of them grow faster than others because maybe they're in a wet spot or a place with more nutrients. And what you find is if you selectively thin, which means you remove the little ones, the big ones grow faster. And you can actually speed up the process, the successional rate at which they get to that old-growth forest. So selective thinning is genuinely an actual possibility for extracting. You can then have your forest and have your economic benefits from selling the wood or conserving the wood. So selective thinning, I would agree, but absolutely not clear-cut forestry, which is happening in a lot of places around the world. People are planting some trees for 5 years, cutting it down, and starting again, and you've missed the entire point.
Ja, da hinten.
That's a good question. Are you talking about my problem of global restoration, or are you talking about the global problem of climate change? When you say this... Yeah, that's, as not a politician, a difficult one to answer, but it's a good one. I agree we need system change. Absolutely, we need to start thinking about how we use resources and how we interact with nature. But I don't think I find that too many people just say this without any tangible plan. I do think technology is a valuable way of getting at that. So in this example that you raised, machine learning was a really nice way of, it's almost like humans have become a dominant organism on this planet because of our unique capacity to learn. But 10 million years ago, we were individual hominids walking around, and the thing that allows us to learn is that we have trial and error, and we have a network in our brain that translates information. Then, as we get older, well, not get older, 10 million years later, or maybe 100,000 years ago, we are later hominids, early Homo sapiens in small communities, and our network is we now have problems at the community level, and we try to address them with our network of communication that allows us to pass on information. So obviously we speed up our ability to learn. We still have the same trial and error. What I love about machine learning and new technology is that we can do that trial and error. We can do 10 million years of trial and error in a millisecond. All it is constantly trying all of the options, and then most of them fail until the one that works, and then you use that one in your prediction. And I do believe that there's a lot of room for technological solutions as we try to come up with these system changes. I'm not saying I know what it is, I think, but as long as you have a targeted end goal of, let's say in your company, you want to reduce emissions from the pasta straightening process. There's certainly machine learning that can help you to target where you're being least efficient, and you can use it to help figure out the maximum impacts with the minimum costs. So I do think technology is going to play an incredibly important role in any kind of systems change, and machine learning is so easy now that everybody's going to be doing it. I don't know if that answered your question at all, but it was a scientist's answer. Yeah.
Hier ist direkt da vorne eine Frage. Ich würde jetzt tatsächlich einmal das Mikro geben, damit auch der Stream mithören kann.
Thank you, it's a pleasure. With regards to science and its role in fighting climate change, I truly believe that science has to be at the core of fighting climate change, but you guys are an example of successful communication, and you managed to get your motto out there and be covered by all the major media in this planet. What would you give as a suggestion, advice to your colleagues so that they do it better on one hand, and then on the other side, how do you think science can solve this problem? Because communication is a huge issue, and we're not benefiting as much as we can from all the knowledge that is out there.
Great question. So, yeah, we do a lot of communication in our lab, and I think the reason that it's been successful is for two very simple reasons that are intimidating to scientists. Because, essentially, the first one is try to address the important questions. There's nobody I would ever speak to in ecology or outside that doesn't think that this is at least vaguely relevant to try and figure out how much carbon can be captured by trees. And there are thousands of those questions available. It's just terrifying to try and address it. No one wants to be the expert. As a scientist, you get so much criticism for any consideration. The bigger the question, the more assumptions you have to make, and the more limitations there are, and the more inaccuracies there are. Like, a global map will be wrong in loads of locations around the world, but will be right on the general trends. So to a scientist, I'd say, stop fearing the bullshit. Just go for the big questions. Because if all scientists were trying to address these big questions of how do you do systems change, I swear we would be way further ahead. But instead, it's much safer to stay in your niche of trying to figure out what species of bacteria sits on the hind leg of a beetle in China. And no one can say you're not the expert at that. It's so much easier. I think it's that fear of not being the expert. Scientists are supposed to be the expert. I will never be the expert on global restoration. No one ever can be. But we can definitely see global patterns. So that's my first part of it. The second one is just don't fear communication. It genuinely is horrible. When any scientific message comes out, there'll be loads of lovely messages, but you're inundated with hate because you made this calculation differently from the way they would, or you just have to not fear it and just go with what you believe. And I think if you stick to what you believe, then it's all good.